Hey guys. All right, this is the video about the chain rule that I told you I would do. So I'm just going to kind of talk you through like just a 2-slide PowerPoint real quick and then work a few examples. The lighting's not great, but hopefully it'll work. And I'm going to use like an interactive whiteboard, and sometimes the stylus is a little unhappy. So hopefully today will be a good day. All right, let me kind of share my screen with you and pull this PowerPoint up real quick. All right, let's see if it's going to be a good day. Oh, look at there, it's a good day. All right, so we're going to go up here and we're going to talk about something called the chain rule. All right, so the chain rule is basically going to give us another way of doing some things. So it's going to kind of expand what we're able to do. So instead of having like single variables to powers, or instead of having like e to a single variable or a trig word with a single variable, we're going to have expressions there. Okay. Now let me kind of explain something to you. All right, here's kind of the idea of the chain rule. Now, first of all, I kind of need you to understand, these are not amoebas. Okay. This is kind of the way a composite function works. Okay. So my domain has some things in it I'm going to call X. And I've got a function G that operates on that X. It makes a new function. And this new function is called U. Okay. So U is the range of this function G. It's what comes out of G. But what's going to happen now is, instead of this being the end, now the end of this is going to be the beginning of this next function. Okay, so X is my domain. It goes in this function G, and the range comes out as U. But the range of G is going to be the domain of F. So what comes out of here goes into here. So I end up going from X the way you normally do to Y, but I have to go through U to get there. All right, it's a little bit like if I work for Nissan and we make cars. Okay, think about a composite function, an assembly line. I don't make the whole car. Maybe there's a part and it comes to me and I put the front doors on. And then it leaves me and goes to the next person who puts the back doors on. So does it make sense that what I end with, this next person starts with? So my range becomes their domain. All right, so the example I always give in class is usually kind of silly, but it's true, and it helps you remember a little bit. When I first graduated from college, I moved to Fort Worth, Texas. Okay, now I'm from a small town in Mississippi called Kosciuszko. So let's just say that I didn't have a lot of experience with big city driving. Okay, so I had an apartment. So the first place I learned to get to was the school I taught at. So I went from my apartment to my school. Now, the next place that I learned to get to was I learned to get from my apartment to the mall. That probably says a lot about me for shopping. Okay. So I could get from my apartment to school and I could get from my apartment to the mall. But it is sad to say that when I first moved there, if I was at school and I wanted to go to the mall, I could, but I had to go back through the apartment. I couldn't go from the school to the mall. I had to go from the school back to my apartment, then my apartment over to the mall. So I learned to do lots of places when I first moved to Fort Worth, as long as I started at my apartment. Excuse me. And if I was somewhere else and needed to go over here, I had to always go back through my apartment to get there for a while till I felt comfortable. So do you understand that my apartment was U? Okay. One place I could get over here to Y, I was at X, and I could get to Y as long as I went back through U. And that's kind of what we're going to talk about in this video. So how do you get from Y over to X or X over to Y? If you don't know a direct route, how to use the chain rule and go through U. So the chain rule basically is the thing on the box. So I need you to kind of stop the video and copy down the thing in the box. So remember, dy to dx is the derivative of the function called y that has an independent variable of x. So what you're going to do is you're going to take the derivative of y with respect to an independent variable called u. And then separately, you're going to take the derivative of u with respect to x. And then you're going to multiply those two answers. And that works on this composite function. Okay, so let me try to talk you through a couple more things. All right, pause the video and copy down these steps for the chain rule. All right, when you get those steps copied down, then unfreeze the video. All right, hopefully you've got those steps copied down because we're going to need them in a second. All right, to work the problems. Now look what it says. It says, I want you to look at the form of the problem. Now, because you're going to have to let u be something. And people always say, well, how do you know what to let u equal? Well, I know what to let u equal because what I want you to do is I want you to become your own fairy godmother. I want you to say, what do I wish u was? And let u be what you wished for, okay? So let me explain to you what I'm talking about. Look at number 1 down there on the example. Now, here's what I'm used to. I'm used to seeing like y is the square root of a single thing, like x. I know what to do with this problem. I would change it to a power and use the power rule. So when I look at this, I see the square root of something. So I would let u be my something. All right. So in that case, we'll talk about in a minute, I'd probably let u be x squared plus 3. When I look at number 2, I see something to the 6th power. And I would let u be my something. When I look at number 3, I see the sign of something. When I see number 4, I see e raised to the something. And number 5, I see something to the 4th power. Okay, so when I look at the form of the problem, that's what tells me what to let u equal because I become my own fairy godmother. Now, let me kind of show you what I'm talking about with that for a second. All right, so let's kind of go back to this for a minute. Okay, I'm going to stop that. And I'm going to share something different with you. I'm just going to share this interactive whiteboard, hopefully. And I'm going to work those problems and show you what I mean. So you have your steps written out. If you don't, then pause the video, back it up, and copy the steps down. All right. So look at the first one on the example. All right. The first one on the example said y equals the square root of x squared plus 3. All right. So when I see that, I see the square root of something. Now think about what we normally do with roots. With roots, we normally change those to powers, and I'm still going to do that. All right. So now I have y is something to a power. All right. So I've got y equals, I've got an x squared plus a 3 raised to a power of 1/2. Okay. So what do I have here? I've got something to a power. So what am I going to let u equal? Well, I'm going to let u equal my something, my x squared plus 3. Because see, when I look at this, here's what I think. Gosh, I wish it was just a single letter raised to a 1/2, because then I would know what to do. Well, I'm going to let that expression be a single letter called u. So it says, look at the form and then let u equal your something. And then it says, okay, now go back and rewrite y in terms of your something. What do I mean? Well, I'm going to use this substitution back over here. Y is going to equal, well, if x squared plus 3 is u, I can substitute x squared plus 3 for u and have u to the 1/2. So I looked at my form. I let u be my something. made my own wish come true. I went back and rewrote, after I decided what to let u equal, I rewrote y in terms of my something, in terms of my u. Okay. Then it says use the chain rule. Now, what do I mean by that? Well, the chain rule remembers this. The derivative of y with respect to x. Remember, this was a y function with x as your variable. Is the derivative of y with respect to u times the derivative of u with respect to x. Now, what do I do next? Well, look what this says. I've got to find some equation that's got y's and u's together. So I start looking. Well, see, that's got y's and x's. That's got y's and x's. That's got u's and x's. This is the only one that's got y's and u's in it. So take the derivative of that one. Well, what's the derivative of a single letter to a power? Power rule says the 1/2 comes down front. My variable stays the same, and my power goes down by 1. So 1/2 minus 1 is a negative 1/2. So I found my equation that had y's and u's, and I took the derivative. Times. Now, find where you have u's and x's together. See, that's y's and x's, y's and x's, y's and u's. Oh, that's over here. That's where I've got u's and x's. We'll take the derivative of that thing. What's the derivative of this function with your x? Well, that would be power rule again. 2x to the first. Power goes down by 1. And then the derivative of 3 is 0. Now, what's my last step? Well, my last step is to substitute back. My original problem didn't have u's in it. I made u up. So I've got to go back and substitute back for u. What was u? U was originally x squared plus 3. Okay. And then you might want to add a step 6 in your notes that just says clean it up, simplified. Now, what do I mean by that? Well, first of all, 1/2 times 2 is 1, so that goes out. So I've got an x left right there. And then I don't like negative exponents, so I've got to move this whole expression down to the bottom. X squared plus 3 to the 1/2. And again, because they gave me the problem with a root in it, chances are when I check the back, it's going to have a root in it. So that's the square root of x squared plus 3. Okay. All right, let's work some more. Okay, so you can always freeze the thing. All right. Take those down in your notes like you're watching me at the board, and then you've got some examples to go along with your steps. Okay, so let's work number 2. All right, look at what number 2 said. All right, number 2 said that you had y was 4x minus 1 to the 6th power. Now, I could do 4x minus 1 times 4x minus 1 6 times and multiply all that out and not use the chain rule. I'm not going to do that. Okay? So remember what I do with the chain rule. Look what step 1 says. Look at your form. I've got something to the 6th power. So what am I going to do? I'm going to let u be my something. My something to the 6th power. So my something is 4x minus 1. See, I became my own fairy godmother. I wished it was a single letter to the 6th power. Well, if I let u be what's in parentheses, then it becomes a single letter to the 6th power. Because I'm now going to put my u in my problem. 4x minus 1 is the same thing as u, so that turns that into u to the 6th. So I made my own wish come true. I do have a single letter to a power. I know what to do with that. So then I use that chain rule, dy to dx is dy to du times du to dx. All right, and just like before, I go looking for which equation has y's and u's. That one doesn't, that one doesn't. Oh, that one does right there. That's the one that's got y's and u's. So what's the derivative of that? Well, that would be 6u to the 5th, power rule, times. Now find where you have u's and x's together. Not there, not there. Oh, that's over here where I have u's and x's together. What's the derivative of that? Well, the derivative of 4x is 4, and then minus the derivative of a constant is 0. Now, I would probably clean that up and have 24u to the 5th. And then your last step is to substitute back, okay? So what was u originally? You made up u. U was really 4x minus 1. So I'm going to go substitute back for u. So u was 4x minus 1. So all I did was substitute back for u what it really was supposed to be. Okay, kind of getting the hang of it? All right, let's do another one. Again, copy these, freeze it, copy down the examples, and then move on to the next one. All right, look at number 3. Number 3 says your y is the sine of 8x cubed. Now, if it were just sine of a single letter like x, I would know what to do. So I wish it was the sine of a single letter. So I'm going to make my own wish come true. See, when I look at that, I see the sine of something. So remember what you do. You let u equal your something. Then you go back to your original equation and substitute u into it. So u is 8x cubed. So in place of 8x cubed, I'm going to put a u. So once I let u equal something and I substitute into my original equation, then I use my chain rule. dy to dx is dy to du times du to dx. All right, so again, you've got to find which equations do you have y's and u's. So I go looking. Oh, that would be that equation. So that's the one I take the derivative of. Well, what's the derivative of sine of an angle? Sine of u, the derivative will be cosine of that angle u. Sine of a single letter is cosine of that same single letter. Times, all right, where do I have u's and dx's together? All right, where I'm looking, where do I have? Right here, that's where I have u's and x's together. So I take the derivative of that. Well, what's the derivative of 8x cubed? Power rule says the 3 comes down. So 8 times 3 is a 24. And then x stays x, and the power decreases by 1. So that's going to be a squared. Okay, can't really clean much up. So usually I tend to put numbers in front, you know, but you've got the cosine of what's u really? Well, it's 8x cubed. Now you've got times 24x squared. Now I need you to understand something. We've talked about this before. This is one thing, so I cannot break it up. So I can't say 8x cubed times 24x squared. That's not real. This is one, this 24x squared times that whole thing. So to keep you from being tempted to do that, you might put the 24x squared in the front. That's what I tend to do. Okay. All right. So copy that down and let's work another one. All right. I've got y equals e to the 5x. Well, see, when I see that, my form is that's e to something. So I'm going to let u be my something. In other words, I wish I had e to a single letter. Well, then let u be something so that your wish comes true. So when I substitute that u in for that 5x, then y turns into e to the u. Then I use my chain rule. dy to dx equals dy to du times du to dx. Okay. So where do you have y's and u's together? The only equation out of your three that have y's and u's is this one. So what's the derivative of e to the x? E to the x. So what's the derivative of e to the u? E to the u times. Now, where's the only place you have u's and x's? Not there, not there. That's over here. What's the derivative of that? Well, the derivative of 5x is just 5 because the derivative of that single letter, remember, is a 1. So usually put constants in front. And then my last step is to substitute back. So put back what u really was. U really was a 5x. Okay, so there's my final answer. We good? Now, number 5 is not harder, it's just a little longer. And here's what I mean by that. All right, when I'm looking at this problem, what I see is I see something to a power. So I'm going to let u be my something. Because I wish I had a single letter to a power. So I made my own wish come true. So once, remember, I'll decide what to let u equal. I put u back in my original problem. I substituted in. So that's going to be u to the 4th. That looks a whole lot better than that thing. Okay. So then I use my chain rule. The derivative of y with respect to x is the derivative of y with respect to u times the derivative of u with respect to x. It's like two derivatives in one problem. So what's the derivative of y with respect to u? Where do you have y's and u's together? That's the only equation out of the three that have y's with u's. So I take the derivative of that. Power rule. 4 comes down, u stays the same, power goes down by 1. 4u cubed. Times, out of my three equations, where's the only one that's got u's and x's? That would be over here. Well, then I got to take the derivative of that thing. But now that thing is a quotient. So I'm going to have to use the quotient rule on it. So when I go do the derivative of this one, it's like a separate problem. All right, what's the quotient rule say? I copy down the bottom. I take the derivative of the top. Well, the derivative of 2x is 2, plus the derivative of 3 is 0. Okay, so the bottom times the derivative of the top minus the top over, all right, so that's the top. Now I got to do the derivative of the bottom. All right, well, the derivative of that bottom, the derivative of x is 1, plus, and the derivative of that constant is 0. Okay. So do we see I've got the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. Are we okay? Now, I'm going to substitute in and clean up. So sometimes I clean up before I substitute. Sometimes I substitute before I clean up. Okay. So what was my u really? Well, my u was really this thing. So I've got a 2x plus, I've got a 3 over an x plus, I've got a 4, and that whole thing is cubed. So all I did was substitute u for what it originally was. Now I'm probably going to multiply this top out. So 2 times x is 2x plus 4 times 2 is 8. And then minus 2x. And then minus my 3. Because 2x plus 1 times 1 is just 2x plus 1. All over x plus 4 squared. Okay. Now let's clean it up. And here's one thing. Do you understand that this cube goes with the top and this cube goes with the bottom? Okay. So do you understand that that's a 2x plus 3 cubed over an x plus 4 cubed? So that cube goes with the top and that cube goes with the bottom. Okay. Now those two x's are going to go out, and then 8 minus 3 just gives me a 5. And then I've got an x plus 4 squared on the bottom. Okay. Now let's clean it up a little bit. Well, I can do remember that 4 is a single number, so I can put it over 1. I go straight across the top. So 4 times that 5 is going to give me a 20. And I've still got this 2x plus 3 quantity cubed. Now, how many x plus 4s do I have on the bottom? Be real careful. Remember we talked about in class, when the bases match, remember you add your exponents. So I've got 3 of them here and 2 of them here. So I've got 5 of them in all. So none of that was hard. It was just a little lengthy. Okay. So this dy to du was real simple. This du to dx wasn't hard. It was just the quotient rule, which remember I told you I kind of avoid because it gets kind of lengthy. It's not hard. It's just lengthy. And then clean it up. Okay. Now, let me make sure you understand, you have been doing this all along. You just didn't know you were doing it. And by that, I mean, what you've been doing are the special cases. All right, think about it. Y equals x to the 8th. You can think of it like x to the 8th. So do you understand? There's no reason to do u substitution, but your u is your x. So if you would never do this, but do you understand? Because you've already got a single letter. But if you did, then y would be u to the 8th. Okay. So your dy, so to speak, to dx would be your dy to your du times your du to your dx. Well, the reason you never do this when there's a single letter, it would be silly. All you're doing is exchanging letters. But see, dy to du would be 8u to the 7th. And then du to dx would just be a 1. So your 8u to the 7th, when you substituted back, would be 8x to the 7th. So we never do it when it's single letters. That would be silly, but you're really just doing a special case. So when you're doing your homework, if it doesn't match one of your basic rules that you've got so far, then you're going to have to let u be something so that it does match one of those rules. So if you've got something to a power, let u be your something. If you've got, y is the tangent of something, maybe a 2x cubed minus a 5. Okay. Well, see, I wish I had tangent of a single letter, but I don't. So I'm going to make my own wish come true. I would let u be my something, the tangent of something. So 2x cubed minus 5. And then I substitute u in my original. So now I've made my own wish come true, because now I do just have the tangent of a single letter. Then I go do my dy to dy to dx is going to be the derivative of y with respect to u times the derivative of u with respect to x. So I have y's and u's together right here. Remember we learned in class last time that the derivative of tangent of an angle is secant squared of that angle times, and then du to dx is over here. So what's the derivative of that thing? That 3 is going to come down, so I'm going to have 6x squared. And then like I told you, so I'm not tempted to do this angle times this. I'm going to move that to the front. So I've got 6x squared times the secant squared of u. You know, community property multiplications, I can change that order. And then the last thing I do is substitute back. And I've got the secant squared of u was really 2x cubed minus 5. Okay, so look at your something. So you're always going to let u be your something and substitute that back in the original. And then you're going to substitute into your chain rule and clean it up. And just don't forget your final answer can't have u's in it because you made u up. Okay, so don't forget for your last step to substitute back what you let u equal. All right, so you can rewind the video, you can go back and take notes, you can go back and look at examples, you can read the section in the book 6.4, I mean not 6.4, 3.4, let's try that again, on chain rule. And then next time I'm going to take about 10-15 minutes max to go over this real quick, and then I'm going to show you a way to avoid the chain rule most of the time if you would rather avoid it. Okay, lots of people use the chain rule all the time. I don't tend to do that, but if you're going to take Cal 2, there are times that you cannot avoid the chain rule in Cal 2. So you have to learn to do it in Cal 1, mainly so that if you need to do it in Cal 2, that you're able to do that. Okay, so you try your homework problems. You got my email address. You can email me and we can make an appointment. I'm happy to help you. So I will see you in class on next time. All right, you have a great weekend.